right, welcome back to Advent of Code Day 4. I think this is a day late or so. Sorry about that. I got caught up with some stuff, but at least I'm getting out. So Day 4 is called Scratch Cards, and the premise is that essentially you're given a set of winning numbers and a set of numbers that you draw, and you want to find out how many of the cards that you drew are contained within the set of winning numbers. And with that, at least in part one, you calculate some point value for your draws, and then that point value becomes your answer. So to be a little bit more explicit, the input you're given comes in the form of, I guess, a string of text, and each line represents a different draw. So for card 1, the winning numbers are 41, 48, 83, 86, and 17. And then the numbers that you end up drawing are these, 7, 8 numbers. And you can see here, 83 is one overlapping number, 86 is another overlapping number, 17 is a third overlapping number, and 48 is the fourth overlapping number. So in this case, there are 4 cards that overlap between your hand and the winning hand. And that means that you have earned 8 points, because the formula used to calculate the point value of your draw is given by the first match that you makes the card worth 1 point, and then every subsequent match doubles the first point value of that card. So essentially, like for card 1, the first match you make, so the 83 gives you 1 point. The 86 makes that now worth 2 points, and then the 17 would make it worth 4, and the 48 would make it worth 8. So you can see here, clearly we're going to need to raise 2 to the power of something to get at the point value for a given draw. So let's go ahead and start coding this. Come over to my VS Code, or cursor I should say, and let's execute the new day script to get the input. And let me grab the test input as well, because this will be useful. So if we head over into or paste this into the test.txt file and then head over into part 1, I'll open up both. And let me make the font size a little bit bigger here, just so it's easier to see. All right, so this is where we'll begin our solution. So immediately we can see there's a pretty standard format for the input, and essentially the approach that I took was just to look at a given line and then start iterating after this space after the colon. So start looking from this character index onward, and then as soon as I encountered the bar here in the middle, I stopped counting these numbers, so on the left side of the bar I counted the numbers as winning numbers, and on the right side I counted these numbers as my numbers or my cards, and I just stored them in 2 vectors, and then those 2 vectors we can just calculate essentially the intersection of those 2 vectors. So let's start by just parsing the input. So we'll iterate through the input lines. So for int I equals 0, I is less than the input size, and I is incremented by 1. Excuse me. We want to start, so for each line we want to define one vector that will store the winning numbers, and then we want another vector that will store the numbers that we drew. So I'll just say drawn numbers. Okay. And then we can iterate through the line itself now, or the characters themselves. So for int, I'll call this character index. And so what I did, and what I think is most efficient here, is to ignore everything before the second space in the input. Because if you look at the test input, so from the test input we can tell that the numbers start always at index 8. So the 4, the 1, and then this space, and the 4, and so on. All of these occur at index 8. And if we look at the real input, the same is clearly true. They begin at index 8. And well, I suppose they begin a little bit later than index 8, but that's okay. So what we can say then is we will start counting. We can start counting from index 8. So for character index equals 8, character index less than or equal to the size of the current line, and we want to increment it by 1. We'll say, so there's a couple of cases that can happen. And just so I type less things, I'll just define a character variable to store the current character. So the first case is the character is a space, right? The next case would be that it is a number. And then the final case would be that it is a vertical bar. Okay, great. So if it's a space, we have two kind of subcases for this. The first subcase is that the previous character was a digit. So let's define a previous character variable and store the character before the current character index. And notice that previous character will always be defined because character index will never be 0. So previous character, if the previous character is a digit, so if STT is digit of the previous character, well, what we want to do now is check, what we want to do is essentially, this tells us that we've, like, for instance, at this space that I'm highlighting here, this expression would evaluate to true. And that would tell us that we've reached kind of the end of a number, or that we've finished defining a number. And that means we want to push that number into either winning numbers or drawn numbers. But the thing is, we don't have a way yet to tell whether or not we should be pushing into winning numbers or drawn numbers. So what I am going to do is introduce a new Boolean value called isLeft, and it will default to true because we always start on the left. We're reading from left to right. And if isLeft is true, then we want to push our current number. And that's the other thing. We don't currently have a place to store the number or the numerical value that we're on, because as we iterate character by character, we're going to have to augment some existing value or some existing integer. So I'll call cur n. It will start as 0, and if we reach this case where we've encountered a space and the previous character is a digit, then we want to push the current n into winning numbers. Great. And then otherwise, if isLeft is false, which would mean that we are now looking at the right side of the vertical bar, then, I called it winning numbers. Then we want to push it into drawn numbers. So push back current end. And then we can reset current n and continue on to the next iteration of this loop. Great. Okay. And then if the previous character is not a digit, so if our current character is a space and the previous character is not a digit, we can just continue, because the only case where that would happen is right here. And we don't care about, well, we care about the vertical bar, but we don't care about this space in particular. Wonderful. Okay. The next case is that our current character is a number. So else if is digit of current character, then we want to basically modify our current n in some way to store this number. And the way that we'll do that, I think I used this in a previous day, is we'll set current n equal to itself times 10 plus the current character casted to an integer. And once again, this syntax is how you cast a character to an integer in C++. The minus 0, not this part. This part just essentially means that as we move, so like we have like the tens place, and then like the ones place, right? Like this is how numbers are formatted in base 10. So like the 4 points to the tens place, and the 1 and so on. So I won't spend too much time on that. It should be fairly straightforward. And then finally, the last case is that we have a vertical bar. So if character equals vertical bar, then what we want to do is simply switch the value of is left to false, and we can continue. Great. And then lastly, we need to handle the edge case, or it's not really an edge case, but because it will always occur, but we need to handle the case when we get to the last the last character in the line. And what we should always do there is you can clearly see that the line always ends on a number. So we need to check if we're at the end. So if character index is equal to input I dot size minus 1. If we're at the last character, we want to simply push the current number. So whether it's 53 or 19 or 1, we want to push that into the drawn cards. Drawn cards dot push back current n. And you may ask, well, don't we have to first modify current n? Well, no, we don't, because here, when we do modify it, you can see on line 53, we don't actually continue immediately. So this code will execute, and then it will come down here and execute this code before moving on to the next iteration of the for loop, assuming, of course, that this condition is true. And then if we are at the end, we can obviously, or if we are at the end of a line, we can obviously stop iterating. I mean, this break won't do anything because we're already at the last iteration, but I'm just including it for additional clarity. And then finally, now that we have our two vectors, we just need to calculate the intersection. So I'm just going to define a helper function to do that. So I'll have a function called intersection that will take in two vectors of integers, one called a and another called b. And then essentially we'll just iterate over one of them. So for int num of a, if std find, and this is just how you check if a element is contained within a vector. I think I probably could have used a set here to make it a little bit faster, but it won't be an issue because we're not looking up, hundreds of millions of entries. We're looking through, 10 or 100 or something like that. And we're searching for num. And as long as that's not equal to b.end, then we need a total here. Total overlaps equals 0, and then we'll just increment this. Total overlaps plus equals 1, or I guess we can use plus plus because we're in C++. And then we'll return total overlaps. Wonderful. Okay, so now coming back into the for loop, on each line we want to calculate the total number of overlaps because that will tell us how many winning cards we have. So int n winning is equal to intersection of drawn numbers, so the numbers that we drew, and the winning numbers, right? And then, so as I mentioned, the formula is the first match makes the card worth 1 point, and then each subsequent match doubles the point value of that card. So it can be easily shown that the formula to calculate the point value of a given number of wins is to say it's 2 to the power of n winning minus 1. It should be noted, though, that this will only work assuming that n winning is greater than 0. So if it is equal to 0, then, because this clearly then would evaluate to like a fractional value, if n winning is equal to 0, we have to just continue on to the next iteration. You could also say like ants plus equals 0. Ants plus equals 0. And I'll probably just keep it like this. And then else we will modify ants. Great. And then I think we should be good to run. So let me cd into day 4, compile the code, and then run it on the test input. And we get 13, which is correct. And then if we run it on the real input, or my real input, we get 26,218, which also looks right. Wonderful. Okay, part 2 is slightly more complicated, but once you see what you have to do, it's actually not too bad. So reading it through, we can see that now instead of counting point values, we want to count how many total scratch cards we have at the end. And the reason that we can't just like look and see we have clearly 6 cards, is because now instead of earning points, winning cards result in duplication of subsequent cards. So what I mean is that card 1 has 4 matching numbers. So you take the next 4 cards, you take card 2, card 3, card 4, and card 5, and you duplicate them each once. So now you have 2 copies of card 2, and each copy has 2 matching numbers. So you win 1 copy, or so for each copy you win another copy of cards 3 and 4, right? So you can think of this, the way that I am processing this problem statement is kind of as a graph, not a like a graph theory graph, but kind of like an axial graph, right? So essentially, one number will tell you how many cards you have to look down, and then the other number will tell you how many like cards. So you can imagine like lining these cards up, right? So let me open up part 2 so I can explain this a little bit more clearly. Essentially, and I'll open up a comment here. So like, let's say for example, you start with card 1 and you win once. So if you win once, that means you win. So yeah, you win once. That means you look down 1 card. So now you're looking at card 2, and let's say you win twice on card 2. Well, so because you looked down from winning once in card 1, now you have 2 instances of card 2, right? So each instance will win twice. Okay. And so that means, let's say you have a card 3 and a card 4, which both win once. So now you've duplicated. So this first card, this first 2 has looked down 2. So it has duplicated card 3 and it has duplicated card 4. And then the second card has also duplicated card 3 and card 4. Not duplicated, added another copy too, right? And you can see how this pattern is going to progress. So the idea here, or the idea that I used, excuse me, is to create basically a vector in which we store, so we'll initialize in which we store the number of cards that we currently have. So a map could have also been used and it would have accomplished the same thing. So essentially though, our vector, so the index will correspond to the card number minus 1, and the element will equal the number of cards that we have. Okay, so every entry in here will be initialized to 1, right? Because we start with 1 copy of every card. So I'll just use a dummy variable here. And this dummy variable will just populate essentially the cards vector, such that we have a vector of the same length of the number of cards that we have in our input, and it contains only elements that are 1s. Great. Okay, so now we have that. And what we can do is we can essentially grab all of our code from part 1. So let me grab first the helper function to calculate the intersection, and I'll paste that into here. And then I'll also grab the for loop that we use to iterate over the input, because we don't have to change too much about it, thankfully. But the only things we do have to change are first, so now, basically, rather than doing this kind of operation, we still want to know how many winning cards we have, but rather than calling these number of winning cards, which it still is, I'm going to call it n copies, because this is how many copies, or I should say n cards below to be copied. That's obviously a very, like, kind of a mouthful, but that's exactly what it represents. It represents how many cards below should be copied. And the way that we'll kind of do this or perform this copying operation is we'll start, so we're going to iterate through the cards array, and we're going to start at our current card plus 1, so we'll start at the card directly after our current card, and we will go until we get to here. And we'll go for this many iterations. We'll go for n cards below to be copied iterations. And we'll go by 1 each time, we'll increment by 1 each time. And for each iteration, we're going to set the card that we're currently looking at, excuse me, or the card that we're like looking at. So I don't know if you remember when I drew out like that little diagram, you know, for 1, we would be looking at card 2. And we're going to set it equal, or excuse me, we'll increment it by cards, by the current card. And so what this means, right, is let's kind of go, we'll walk through an example here. So in card 1, you win 4 times, right? So what that means is n cards below to be copied equals 4. So you start iterating through the cards vector at index 1. So that means cards 2, 3, 4, and 5. So before this loop, the cards vector looked like this, but now it's going to look like this: 2, 2, 2, 2, and then I guess 1 is still at the end. Great. And so you can see now when we look at card 2, because this essentially serves as like a multiplier, right? But the nice thing is we don't actually need to perform any multiplication. All we have to do is at the end, we just have to sum the frequency of each card. And luckily we have the frequency of each card stored in a vector here. So we just have to sum across this vector. So we can say for int card of cards, and this is iterating through the elements of cards rather than the indices, we can just add that value to the answer. And this should be exactly what we need. So if I compile part 2 and run it on the test input, I get 30, which is exactly correct. And then if I run it on my real input, I get, what is that? 9,997,537. That looks right. Great. Well, I hope today made sense. I'll do day 5 tomorrow. I think I'm, 1 day behind schedule, but that's okay. Thanks so much for watching, and I hope this was helpful.